Metrology is a science of precise and retraceable measurement. And in the past, measuring with a higher precision has always opened up a window into a new world and increasing our knowledge. There are a few very interesting examples on that. One, for example, is Professor von Klitzing. He formerly was a student here at TU Braunschweig and also working at the Physikalisch-Technische Bundesanstalt, our strategic partner here at Braunschweig, the second largest national metrology institute in the world. And he was also working there, being infected with the precision measurement, so to say. And later on, he has measured the resistance of transistors in a magnetic field and has analyzed very tiny deviations from the conventional behavior. And by that, he has detected the quantum Hall effect by his precision measurements. And the quantum Hall effect was awarded with a Nobel Prize in 1985 and is nowadays used as a standard for resistance. A second example, also very interesting, is the work of Professor Hensch at Munich. He has measured the color of light with a very, very high precision, up to 18 orders of magnitude. And you would ask, why do you want to measure the color of light with such a high precision? But as a matter of fact, if we are watching the light from remote solar systems, then we can analyze the frequency of these stars, and this frequency is varying depending on whether or not a planet is orbiting in the solar system. So by very, very tiny deviations from the core frequency of the solar system, you can see whether or not there are exoplanets. And this has also led to the Nobel Prize in Physics and finally to the detection of many, many exoplanets, and basically changed our whole view on the probability of life in outer space, let's say. A third example is the development of super-resolution microscopy, and this has been done at Stefan Hell's group in Göttingen. He has also been awarded with a Nobel Prize in chemistry, and there the problem is that in a conventional optical microscope the resolution is limited by optical diffraction. There you can reach only about 500 nanometers of optical resolution. And now if you have an object which is not illuminated all at the same time, but emitting light as a function of time from different positions on the object, then you can analyze the signal as a function of time and convert it into an image as a function of real space. And by that you can dramatically increase the resolution of such super-resolution microscopes down to 10 nanometers and watch, for example, mechanisms inside living cells. Also a very exciting metrological advancement which has opened up a completely new window into a new world which is now possible to observe. Well, nanometrology is metrology of the very small nano objects. And this is important if you want to watch single molecules, single bacteria, for example, in healthcare, in environmental analysis. And if you think about it, there is a certain strong discrepancy between the digital world and the real world surrounding us. In a digital world, we have all the information at hand immediately. Like, for example, we could right now find out whether the train between Shanghai and Beijing is delayed or not. Whereas we have basically no information of the real environment here in this room. So what is the air quality? What is the water quality? And the reason is that there are no sensors available which are measuring all that. And these nanosensors should measure air quality, like nanoparticle exposition here in the room, everywhere in the city, to give a good feedback of the quality of the environment. And this is our goal in our nanometrology center, where we want to develop such sensors. And these sensors not only have to be able to measure these things like nanoparticles, like NOx exposition and so on, but they also have to be ubiquitously available, which means that they have to be cheap, they have to be available for everybody, maybe at the end even in smartphones, so that you can really have immediately everywhere a signature of your environmental quality all over the world, basically. QuanOmote is a research initiative of both universities of Hannover and Braunschweig University of Technology, together with their core partner, Physikalisch-Technische Bundesanstalt here at Braunschweig, the second largest national metrology institute in the world. and it's part of the Hannover Braunschweig Research Alliance, one of 3 core research areas where we combine our competences in quantum technologies, mainly on the Hannover side, and also in nanometrology, mainly on the Braunschweig side. We're working, for example, on gravitational wave detectors. We are working on atom traps for precision measurements in space. We are working on nano LED arrays for super resolution microscopy. So we are basically combining all our competences which have been brought up over the years, both at Hannover and Braunschweig. And for example, at the core of all these activities are 2 research centers, HITEC at Hannover and LENA, the Laboratory for Emerging Nanometrology here in Braunschweig. So we have an excellent infrastructure. We are convinced that we can create an internationally renowned center for quantum and nanometrology by combining both competences from Hannover and Braunschweig. And this exciting strategy will carry us also into the future. There are more than 50 people working in this core research area, and the Research Ministry of Lower Saxony is funding QuanOmote over the next 5 years and giving us the chance to hire up to 40 additional researchers, and they will work on enhancing and pushing forward the frontiers of quantum and nanometrology and opening new windows into new worlds of the smallest, like single molecules, and the largest, like, for example, gravitational waves.